Welcome back to Math 103. This is video number 28 on growth and finance. The common theme of the financial problems in this chapter is that money deposited in the bank and left there, and not taken out, accumulates interest. Similarly, money that's been borrowed, but not paid back, accumulates interest. As a result of accumulating interest, it grows by a certain percentage at regular time intervals, which means that it's multiplied by a certain growth factor at regular time intervals. So this is the common theme of problems in this chapter, but there have still been different problem types, and there's always this question that we face: how do you identify which problem type, which situation you're looking at? In the context of these problems about money growing over time as a result of interest accumulating, there are two key distinctions. The first one is between situations involving a one-time payment and ones involving multiple payments. So some situations involve a one-time payment, and that's where we used the compound interest formula. We spent a lot of time at the beginning of the chapter developing and applying the compound interest formula, and each time we did so, it was to a one-time transaction. You deposit money in the bank once, and that one deposit grows over time into something larger. Or you borrow money once, and that debt grows over time into something larger. By contrast, more recently, we've been looking at these annuities. So these involve multiple regular equal payments, each one of which is its own mini compound interest formula problem. But when we string enough of them together, we're then really dealing with an annuity. So you always look carefully at the beginning, which of these situations are you in? Once you know that you're dealing with an annuity, there is a second key distinction. Some annuities involve many payments accumulating to a large sum in the end. So all of our problems involving saving up towards some goal in the future, where there's a big amount of money at the end of the process, that is one category, and that large sum of the end is called the future value of the annuity. So certain kinds of annuities involve payment, large sum at the end. In those situations where the payments come first and the accumulated amount is at the end, it's a job for this formula right here. We want to know how much is that future value, that accumulated value at the end. Well, it is determined by the amount of each payment and the interest rate per payment period and the number of payments. In this formula, N means the number of payments. Just as a matter of terminology, this category of annuities is what we mean by fixed deferred annuities. By contrast, there is a different type of annuities, and we call those installment loans. This other type, and this is the key distinction, this other type involves a large sum changing hands at the beginning of the process, and then many small payments following it, such as, and this is the key example, a loan that you take out today, which is then gradually paid off over time. In this case, you've got large sum changing hands, then payment. That large sum is called the present value of the annuity. So that is the second key distinction that you always look for. Once you know that you're looking at an annuity, you ask, are the payments coming first and then the large amount at the end, or is the large amount changing hands at the beginning followed by the regular equal payments? Let's look now at how installment loans work. Now, earlier we looked at the example of someone, a friend of yours, but surely not you, who borrows a new $250 every month and then lets the debt accumulate into a large sum at the end. So your friend is not making any payments, your friend is just borrowing more, and then the question is, how much debt is there at the end? That large sum at the end, in that example, that was a future value, and the computation was a job for this formula. But now we want to change perspective and think about borrowing a large sum at the beginning, a large sum in the present, and then making regular payments until the debt is repaid. This is a different type of annuity. Your friend received $250 at a time, multiple times, and then there was a large amount at the end, and here, by contrast, there's a large amount at the beginning, followed by payment. The setup here really is different, and we're going to need a formula for the present value instead of the future value. What we're discussing here is a very important real-life application. The typical setup of student loans, car loans, mortgages, other types of loans is that the borrower receives one large sum in the present and subsequently makes regular payments of the same dollar amount in each payment until the loan has been paid off. Couldn't you have a loan where it wasn't the same dollar amount getting paid back each time you made a payment? Yes, that's possible, but typically they are set up in this way. For many loans, these regular payments are made monthly, but it's also possible that you could have quarterly payments or loans with weekly payments, daily, semi-annually, etc. Most common, though, in these kinds of situations is that the payments are made monthly. Now, our goal here is to understand how the following quantities are related to one another. The amount you borrow, the present value that we denote PV, the dollar amount of each payment, that's denoted PMT, the interest rate per time period, that's in decimal form and denoted I, and the number of payments you make before you finish paying off the loan, and that's denoted N. In other words, PMT, I, and N are going to mean the same thing now as they did in the future value situation. We'll work up to this by first taking a step back and looking at something simpler, namely a loan which you repay with one large payment instead of many small ones. If you can repay $3,000 1 year from now, and the interest rate is 9% compounded annually, how large a loan can you afford to take out now? So you borrow an unknown amount that you're trying to figure out now, and a year from now, that debt will have grown into $3,000 based on 9% annual interest. Okay. You've already done problems like this. So before going on to the next video, find the answer to this question.